Okay, good morning, students. So let me continue with. Uh, so this was last lecture. Yes. So we were proving this theorem about normal operator. So if we have any normal operator on a complex Hilbert space, uh, so if we have any complex Hilbert space and T is any bounded linear operator, then the first result was T is normal if and only if norm of Tx equal to norm of T star x, and the second one is if T is normal, then norm of T to the n is equal to norm T to the n for every natural number n, and also this kernel of T, kernel of T star are equal, and it's equal to the orthogonal complement of image T and image T star. So, one comment. So I said that for this one way, if like the norm of Tx is equal to norm of T star x, then you will get that uh, T star T minus T star x inner product with x is 0 for all x, and then we say that this will imply that this is 0 operator, and therefore T will be normal. So for this I said that on any complex Hilbert space, if we have Tx with x for any linear operator, if Tx inner product x is 0 for all x, then T has to be 0. So, this actually follows by this equality that 4 times inner product of Tx with y is equal to this thing. And if you see Tx with x is 0 for all x, then the right hand side, all the terms are 0, and therefore the inner product of Tx with y will be 0, and this will imply that T is 0. So last time I wrote wrongly that to prove this you use polarization identity. This you can prove just by expanding this right hand side, and then you see that all the terms will cancel and you will get only this 4 times inner product of Tx with y. In fact, this is more general than the polarization identity. You can see that you get polarization identity from this identity by taking T to be the identity operator. So if I take T equal to I, then this will give 4 times inner product of x with y is equal to, the first term will be inner product of x plus y with x plus y, which is norm x plus y whole square, minus this will become norm x minus y whole square plus I times norm x plus iota y whole square minus iota norm x minus iota y whole square, which was the polarization identity. So this is in fact more general than the polarization identity. So you will need only linearity of T and then the properties of inner product to get this. So now, so one part was left. So let me write this again as a theorem. So we want to prove this, that if T belonging to B of H is a normal operator, which means that T star T is equal to T star, then norm of T to the n is equal to norm T whole power n for every natural number n. So to prove this, first we will prove that this is true if T is the self-adjoint operator. So first we will show that if T is self-adjoint, T star equal to T, then norm t to the n is equal to norm t raised to power n for every n in n. So to see this, first you notice that this is true for n equal to 2. Right? So why this is true? So if I take since t star is equal to t square, I can write as t star t. So therefore norm of t square is equal to norm of t star t, and we know that for any bounded linear operator, norm of t star t is equal to norm t square. So this is true if n is 2. For n equal to 1 it is trivial, and it is true for n equal to 2 also. Now once it is true for n equal to 2, then it will be true for n equal to 4 also. Right? So now by induction, effectively norm of t raised to power, if I take any power of 2, this is equal to norm t raised to power 2 to the k for every k belonging to n. Right? You just use this equality for t square. So if I have t to the 4, then that is t square squared. So norm t to the 4 will be norm of t square squared, and norm of t square is again norm t whole square. So that is norm t to the power 4. And then by induction, this will be true for any power of 2. So now we have to show that this is actually true for every natural number n. So if I have any natural number n, if n is any natural number, let k be such that n is less than equal to 2 to the k. So then norm of t to the power 2 to the k, this I can write as t to the n times t to the 2 to the k minus n. And now we use that norm of t1 t2 is less than equal to norm t1 norm t2. So this will be less than equal to norm t to the n times norm t to the 2 to the k minus n. And for the second term, we can write this as less than equal to norm t to the n times norm t raised to power 2 to the k minus n. This was norm of t to the 2 to the k minus n. And the left hand side is nothing but norm t raised to power 2 to the k. So this is equal to norm t raised to power 2 to the k. So this implies norm of t to the n is greater than equal to norm t raised to power n. And the other inequality we always have, that norm t to the n is less than equal to norm t to the n. So therefore we get this, since norm t to the n is less than equal to norm t raised to power n is always true. We get norm of t to the n is norm t raised to power n. So we have shown that for self-adjoint operator, norm of t to the n is equal to norm t raised to power n. Now we have to prove that it is also true for any normal operator. So now if t is any normal operator, for any t belonging to BH, t star t is self-adjoint. So let's apply the previous result for t star t. So therefore, norm of t star t raised to power n is equal to norm t star t raised to power n. This is true for every natural number n. Now what is t star t raised to power n? So if t is normal, t star t raised to power n is same as t star raised to power n times t to the n. For normal operator, t star and t commutes. So if you have t star t multiplied n times, then you can take t star multiplied n times t raised multiplied n times. So this is not true if t is not normal, but for normal operator this is true. So therefore this left hand side I can write like this, and what is this t star t raised to n? T star t norm is same as norm t square. So this is equal to this. I can also write equal to norm of t raised to power 2n. So therefore, norm t raised to power 2n, this is equal to norm of t star raised to n times t to the n, which is less than equal to norm t to the n times this norm t star raised to power n is less than equal to norm of t star raised to power n, but norm of t star is same as norm t. So this again is equal to norm t to the n times norm t raised to power n. So what do we get from here? This implies norm t to the n is bigger than equal to norm t raised to power n. And again we have that norm t to the n is less than equal to norm t to the n. So this will imply norm t to the n is equal to norm t raised to power n. Okay, so this is one important fact about normal operator, that norm of t to the n is equal to norm t raised to power n. And later, if we talk about spectral radius of operator, then we will see that this will imply that spectral radius of t for normal operator, spectral radius of t is equal to norm t. So that will follow easily from this, and uh, formula for the spectral radius. So okay, so let me know. So later we will talk more about this self-adjoint normal operator, etc. But right now let me talk about orthonormal sets and orthonormal basis for a Hilbert space. So now we'll talk about orthonormal sets and orthonormal basis. So orthonormal, you must be knowing the definition already. So let's define. Let H be a Hilbert space and let I be an indexing set. So this indexing set, it may be uncountable also. So I'm writing I for the indexing set. Now subset S is equal to UI, where I in I. This is said to be orthonormal if there are two things. So one is that this set is orthogonal. So if inner product of, or I can write in one way only. So if I take any ui and uj, the inner product of this is equal to delta ij. This delta ij is the Kronecker delta function. So delta ij, which is equal to 1 if I is equal to j and 0 if I not equal to j. Right. So the inner product of any two distinct elements from this set is equal to 0 and norm of every element is equal to 1. So each vector is a unit vector and they are pairwise orthogonal. Now one easy thing to check is that if we have any orthonormal set, then it has to be linearly independent. So this is an easy fact that any orthonormal.
So why we are taking Hilbert space? Like we can just take only inner product space itself.
Yeah, this can be defined for any inner product space. So here I don't need to, but later we will talk about Hilbert space. So here let's say this is an inner product space. Yeah. So any orthonormal set is linearly independent. So this is very easy. So to prove that it is linearly independent, if I take any finite linear combination equal to 0, then I have to show that all the scalars are 0. So if we let summation of Ci ui I equal to 1 to n. This is equal to 0, where this u1 u2 un is any finite subset of this S. Then we have to show that all Ci equal to 0. So by taking the inner product with uj, so then summation Ci ui inner product with uj, this is 0 or j equal to 1 to up to n, and this implies we know that this inner product will be equal to Cj. So Cj equal to 0 for all j equal to 1 to up to n. So this implies that this is linearly independent. So next is right. So let's recall the Gram-Smith orthogonalization process. So what it says is that if you have any linearly independent set in an inner product space, then you can make it into an orthonormal set. So suppose I have any inner product and let x1 x2 so when you have studied in linear algebra, then we take any if finite set of linearly independent vectors and then we make it into an orthonormal set. So this can be done for countable also. So suppose I have x1 x2 xn and so on be a linearly independent subset of any inner product space. So be a countable linearly independent subset of an inner product space, then there exists an orthonormal So let's call this E1, E2, and so on. So an orthonormal set E1, E2. Again, a countable orthonormal set such that if I take the span of this x1, x2 up to xn, this is same as span of E1, E2, En. This is true for every n. Right. So let's recall how we get this orthonormal set. So the proof is simply that we have this x1, x2, xn are given to be a linearly independent set. So each xi is non-zero. Right. So now what we do, first of all, E1, you just take E1 equal to, you just you normalize the x1 vector. So x1 by norm x1. This is our E1. And then uh, I have E2. So what you do is now you get a unit vector E1 which is in the direction of x1. So now you want E2 to be orthogonal to E1. So what you do is you look at this x2 vector, and then you have this is E1 vector. So you just look at the projection of this x on this in the direction of E1, and then if I subtract that, then that will become orthogonal to this. So what is that vector? So that is simply x2 minus x2 inner product with E1 times E1. If I do just x2 minus x2 inner product E1 with E1, then this becomes orthogonal to E1, because if you take the inner product with E1, then you see that x2 E1 x2 E1 cancels and you get 0. But this vector need not be a unit vector, so you divide by its norm. So this divided by norm of x2 minus x2 E1 E1. Again, note that this norm of this vector uh, is non-zero, therefore I can divide by this. Why this is non-zero? Because if this is a zero vector, then you get that x2 is a multiple of E1. So that will show that x2 is a multiple of x1. But x2 and x1 are linearly independent, so that is not true. So therefore this is non-zero. So we get this. And then inductively you can define. So then what we have, so then this E1, E2, this is orthonormal. And what is the span of E1, E2? That is same as span of x1, x2. Right, because E1 is just a multiple of x1, and you see that E2 is a linear combination of x2 and E1, but E1 is a multiple of x1, so E2 is a linear combination of x1 and x2. So both E1 and E2 belong to a span of x1, x2. So we get this. Right. Now once we have uh, E1, E2 up to say En, then I can construct En plus 1. So if we have E1, E2 up to En chosen, then we take En plus 1 is you take xn plus 1 and then from that you subtract the inner product of xn plus 1 with ej j equal to 1 to up to n, right? So this you are subtracting the projection in the space spanned by this E1, E2, En, then this becomes orthogonal to xn plus 1, and then you this vector belongs becomes orthogonal to each E1, E2, En, and then you divide by its norm to get unit vector. And this will give you and this will give you a orthogonal sequence E1, E2, En, and so on. And then span of for any x1, x2 up to xn is same as span of E1, E2, En. Okay, so then let's look at next proposition. So this says that suppose I have E1, E2 up to En. So if I have any finite orthonormal set, be an orthonormal set, then for any x we have that summation of x inner product ei is mod square I equal to 1 to n. This is less than equal to norm of x square. And also if I look at x minus summation x ei I equal to 1 to n, this is orthogonal to ej for all j equal to 1 to up to n. So how do we get this inequality? So we look at this if we look at x minus this vector x ei, this norm square, this is greater than or equal to 0, and then we write this norm squared as inner product of this with itself. So this will give x minus summation x ei inner product with the same vector. And then when you expand this, then we get this is equal to x inner product with x, and then we have we will get so minus we have this summation so let's write minus x inner product with summation I equal to 1 to n x ei ti, and then minus summation I equal to 1 to n x ei inner product with x, and plus when we take the inner product of these two vectors, then because e1 e2 en this is orthonormal, so we'll get summation I equal to 1 to n mod x ei this square, right? Because when we take ei inner product with ej, that will be equal to 0 if I is not equal to j, and for I equal to j we get ei inner product with ei that is equal to 1, and then we have this is scalar, and here in the second component it will come as complex conjugate, so we get this. And then what is this equal to? So again here if you see we will get this is this will come out as complex conjugate, and then we have x inner product with ei, so that will become mod of this inner product square, and here again we get this same thing. So this is equal to norm of x square minus summation mod of x ei square I equal to 1 to n. Because all these three terms are same, so one will cancel with this, and then you get only this. So we get this, and therefore we get the its inequality. So geometrically note that what this is saying is that if you have any vector and you take the projection along these unit vectors e1, e2, en, then the norm of x square is bigger than equal to sum of this, right? So if you have only one vector, then you see you have x, and then e1 is here, so this mod of x dot ei e1 this gives you this projection. So by Pythagoras theorem you know that norm x square is equal to this square plus this square, so norm x square has to be bigger than equal to this. So same thing is true that if you have in 3 dimension you have take projection along the x axis and y axis, then any vector x norm x square will be equal to x1 square plus x2 square plus x3 square, and this is nothing but x1 square plus x2 square, right? So this is not very surprising result. So we get this, and this orthogonal to EJ is again just by checking. If we look at x minus summation xei ei inner product with EJ, then this is equal to x with EJ minus summation I equal to 1 to n xei, and then we'll get ei EJ, but this is equal to delta ij. So this will be non-zero only when I is equal to j. So this gives xej minus xej, which is equal to 0. So now the next result is if we have any inner product space, let H be any, again we don't need completeness, if it is any inner product space, and let ei I belonging to some indexing set, this be an orthonormal set, in H. Then for any x in H, this set S is equal to I in I, such that xei is non-zero. This is at most countable. So why is this true? So we are saying that if we have any orthonormal set, then except for like countably many this I, the inner product x has to be like orthogonal to ei except for countably many i's. So x dot ei, this can be non-zero only for the countable set. So to see this, let's look at this set Sn. For any n in n, Sn is equal to all those I such that the inner product of xei mod square is bigger than norm x square divided by n. So then what can we say about this set Sn? How many elements can it have?
Strictly less than n.
Yes. So by the previous result, by the previous proposition, this cardinality of Sn has to be less than equal to n minus 1, because suppose it is greater than equal to n, then if we look at the sum of for this thing u1 e2 up to en, then we know that from the previous one that norm x square is bigger than equal to this thing, but each of this thing is greater than uh, norm x square divided by n. So if there are n such thing, then we will get that norm of x square is strictly bigger than norm x square. So that will be a contradiction. So it can have at most n minus 1 elements. And this is true for every n. Now what is this set S? So since S is equal to union of Sn, n equal to 1 to infinity, because S is all those I such that the inner product of x dot ei is non-zero. So if it is non-zero, then the mod of x minus ei square, this has to be strictly bigger than norm x square by n for some n. So S is equal to union of Sn, and each Sn is a finite set. So this S is countable. And of course, S can be a finite set also, but it cannot be uncountable set. S can be even empty, like if you take x to be the zero vector, then that is orthogonal to every ei. So in that case, this set S is actually empty set. So okay, so now, so we know that this x dot ei, this can be non-zero for at most countably many i's. So we can now talk about summation of x dot ei mod square, where I in I, because I know that this thing is non-zero only for countably many i's. So of the countable sum we can do, right? So so using the previous result, we can make sense of summation x dot ei mod square I belonging to I for every x in H, because I know that this quantity is non-zero for at most countably many, and countable sum we know how to do. So what we do is that if S is empty set, then this is equal to 0, and if S is finite set, then we will have finite sum. So if S is equal to say I1, I2, I n, then this is just this finite sum x dot eij j equal to 1 to n, and for countable again we just take the countable sum. Sum I1 I2, this is a countable set, then this is summation of j equal to 1 to infinity of x dot eij and this sum will in fact be a finite sum. So this infinite sum always converges. So that is by this next result. This is called Bessel's inequality. So this says that the summation of, if we have any orthonormal set, if I in I is an orthonormal set, then summation of mod x dot ei square, this is less than equal to norm x square. So this follows from this previous one, that we showed that for any finite set of orthonormal, any finite orthonormal set, we have this inequality, right? So if we want to prove this, proof is, we know that this is non-zero only for at most countably many. So if this set S is finite, then we will get only finitely many vectors, and we have x dot this mod square, and then by that proposition we know that this is less than equal to norm x square. And if it is a countable set, then to show that this sum is less than equal to norm x square, we have to show that if I take j equal to 1 to any n, then the sum has to be less than equal to norm x square. So again, that will give us a finite orthonormal set, and then by that proposition we have this, right? So the proof, this follows by the proposition that this summation of I equal to 1 to n less than equal to norm x square, right? So So just like we did in this previous one, we wrote x minus summation of x dot ei. This vector we said is orthogonal to ej for every j equal to 1 to n. So similarly, for any this orthonormal set, we can talk about x minus summation of this x dot ei, where I in I. So that will be a vector in the space, and we'll see that that is orthogonal to each ei. So first of all, how to like make sense of this sum x dot ei, where I in I. So again, because we know that x dot ei is non-zero for at most countably many, so that sum which is like maybe uncountable sum also, that can be reduced to just a countable sum. So we just have a countable sum. So we can make sense of that by, so if I have the space H is complete, then you can show that this will become a Cauchy sequence, and then by the completeness it will converge. So one can define the limit of this summation I equal to 1 to infinity, and then we will see that. So I don't have time, so next time I'll write down that part, and then we'll see that for any Hilbert space, it has, so we will define what is known as an orthonormal basis, so which is maximal orthonormal set. So that it will be called orthonormal basis. And then by John's lemma, one can see that every Hilbert space has an orthonormal basis. And then we will see some more result about orthonormal basis. So we'll meet again on Thursday. Friday is a holiday. So this week there will be only one more class on Thursday. Okay. Any quick question? Okay, let me stop then.